Let's keep going with chapter 2.3. Now that we know a bunch of basic derivative rules like constant power functions, exponentials, sine waves, let's look at some other functions. I've heard, not sure it's true, that not every sine wave has an amplitude of 1. So what if we had an amplitude of something other than 1? So for example, what if we had f of x equals, how about 5 times sine of x, an amplitude of 5? What would you guess that the derivative is going to be then? This is a good time to pause the video, go check it in Desmos, and then come back. All right, welcome back. Let's go try it in Desmos. F of x equals 5 sine x. And we can just ask Desmos to graph f prime. And what do we notice about f prime there? Think about that. It seems to be kind of a cosine wave. I mean, it starts high and moves down. Is it just plain cosine? Well, it starts at 5 instead of 1. So our guessed derivative would be 5 cosine x. And if I turn that off and on, it seems to exactly overlap f prime. Could be more careful, but it seems pretty convincing. So what's going on there? We stretched the original function vertically, and the derivative function was stretched vertically as well. So another way to think about this is to graph the tangent line. Let's do L of x equals, try to remember what the tangent line formula is, our best local linear approximation. It's f of c plus f prime of c times x minus c. And again, right now we're just depending on Desmos to compute f prime for us. Let's plot the point c comma f of c. I've been usually doing that in black, and this one we'll do in black as well. And let's move it over here just because negative slopes are good too. And we haven't really said what happens if we change the amplitude, so let's put a constant like k in there. And now as I increase the amplitude by sliding k, the tangent line is helping point out that the graph gets steeper right there as we increase k. What's another good math question to ask at this point? Well, if I use a k value less than 1, does my tangent line get less steep? That seems to be good. And what's another good question to ask at this point? Think about it. How about negative k? So what do you think will happen if we push k into negative territory? Make a guess. Ready? Here we go. Did your guess turn out to be right? So all together, let's put this down on paper as our constant vertical multiplier rule. K is a constant here compared to x, and we're multiplying in a way that stretches the vertical scale. So let's switch back to pen and paper. Okay, we found that f prime of x was equal to 5 times cosine of x. So we kind of copied the 5 and took the derivative of the sine. That was exactly true. So let's write the constant vertical. Now the book just calls it the constant multiplier rule because that's what all the books call it, the constant multiplier rule. But I want to emphasize that it's the constant vertical multiplier rule. So it is, if you have k times some function, derivative of that, where k is a constant, go ahead and take a sec to think, how can I write a new formula here, kind of like that one that tells me what to do. Pause in 3, 2, 1. Okay, welcome back from pausing. So maybe you came up with something, maybe you didn't. But I have two proposals for you. to think about. Which one of these would you say is true? Can I kind of distribute the prime and put it on both the f and the k? Or do I put the prime just on the f and not the k? Take a sec to think about that. Well, what is k prime? If k is a constant, then k prime is 0. So if I did it k prime times f prime, that would just be 0 times f prime, and that would just be all 0. So this one does not end up working out. That ends up so simple it's not even right. So this one is indeed the constant vertical multiplier rule.